Hello, hackers. Let's get this camera as I wave to you all. Awesome. All right, let's get rolling. We've got a big challenge for us because last time I had to run and Connor noobed up our awesome puppy.s, where apparently it doesn't work. So now this is super awesome. You're going to see me trying to debug code that I don't remember writing, in this case, because I didn't write it, trying to figure out a bug and fix the bug in assembly with the tools available to us. So, as a reminder, we got puppy.s, and puppy.s implements this basically cat, right? With cat, you can cat a bunch of files like /flag, or you can cat multiple files or just multiple instances of the same file, and it just prints them out to standard out, and this is all great. We went to write cat in assembly. First, we wrote a mini version called kitten, and then in C, and then we tried to re-implement that in assembly, and it all worked until we tried to add okay, original file may have been changed. Let's just see what's going on here. Okay, we're just gonna pretend not what. Oh, did you do that? Yeah. This is your code? Our while header, our big loop. Yes. Yeah. So we ran into issues where we tried to go from just opening the first argument to supporting multiple arguments on the command line in this style. Flag, etc pass WD, and this should print out both the flag and the contents of etc pass WD. But if we build puppy and do flag, it works. If we do two things, it only does one. Interesting. So now we're going to try to figure out what the hell is going on. And first, we're going to basically reverse engineer puppy, because now I don't know this code anymore. So I'm going to go through and I'm going to try to make comments about what's going on and see if we can spot the bug this way. If not, we're going to dive into GDB and figure out what is going on there. Actually, before we do this, quick update on where the class is. This is the last half week of the Computing 101 module. So if you haven't done the assembly, if you haven't started on building a web server yet, you are a little bit behind the curve. Please make sure that you can start on building a web server, giving yourself enough time to get through it. Okay. Awesome. So that being said, let's dive in here. So two sessions ago, we figured out that when the program starts up, RSP is pointing to the stack. And again, if that is a mysterious concept to you, please watch the videos of this module. RSP is pointing to the stack, and two quad words, that is 16 bytes into the stack to the right of where RSP points, is the address of the first argument of argv1. So 8 keywords into the stack is the address of argv0, which is our the name of our program. Awesome. So here we did we grabbed this RSP value. For some reason, we put it into R10. For some reason, into R11, we put the number 16, and we subtracted 1 from R10. So I have no idea why this occurs, but we're going to GDB it and try to understand. Then we enter this big loop called our big loop. We compare R10 against 0. And if R10 is 0, we exit. Okay. So I already had confused myself, assuming that here we're loading the address of the argv1 string. But if we GDB this, and we start and we set disassembly flavor and tell, and we disp3i RIP. And actually, while we're here, what happens if I put in a emoji in here? Doesn't like it. Okay. While we're here, let's just take this and put it in GDB init. So we can do set disassembly flavor intel, disp3 instructions every time we stop. And you know what? If I remember correctly, history save on. Is this going to work? GDB puppy. Awesome. What we do is df, and then did it save my history? Yes, now we have a history saving. Okay, perfect. So now we can do start I. Perfect. It's an intel. Everything is good. So if we can do info reg, but let's just px rdi, px r10. Of course, it's all 0. We just started out. Here we go. The only thing that's set is the stack pointer and our instruction pointer. And here's our first moving of RSP, not RSP plus 16, moving of RSP. What is RSP? Let's step over this. And then let's see what RD R10 is. R10 is the value 1. Awesome. So there's number 1 in R10. Now, what is this? I know that this is the number of arguments, including the program name. That's the first thing on the stack. So if you go A, B, C, launch this program puppy with 3 arguments, we restart it, we step. Why is my display not working? We step here, and we look at what RSP is now. No, not RSP, R10. It's 4. Puppy, A, B, C. 4 arguments. All right. Now things are starting to make sense about the code that Connor wrote here into my beautiful puppy. He is reading the number of arguments that are passed onto the stack, loading them into R10. For some reason, loading 16 into R11. Not sure why yet. And then subtracting 1 from R10. I'm guessing the subtraction of 1 from R10 is to get rid of argv0. Right? argv0 is the name of the program. We don't want to cat out the program itself. That's going to mess up our terminal. So here, there's a malicious comment that's trying to mislead us. I mean, it's not false. RSP plus 16 has the address of the first argument, but that's not hyper relevant here. What we're doing here, so this is kind of like general notes, right? But what we're doing here is something like int numargs, which is R10, equals argc in C++ terms, right? Awesome. That's now this guy. What the hell's going on here? Not sure yet. Let's see how it's used. And then here, it's argc -1. So let's do that. And then this one, we don't know what's going on yet. So let's keep going. All right. So if we compare R10 against 0, so I'm guessing Connor wants to keep outputting stuff until we and probably there are more subtractions from here somewhere. R11, add R11, sub R10, 1. So as he ticks down the number of, every time he outputs a file, he's going to decrement this guy. Now, sub R10, 1 is great, but we can also do something like dec R10. This decrements R10 by 1. It is such a common operation, incrementing and decrementing, that Intel designed it into the instruction set architecture. You might hear a lot of misguided reduced instruction set architecture versus complex instruction set architecture bullshit arguments. And people say, yeah, x86 is bad because it's CISC, whereas ARM and whatever other crap, MIPS and so forth, is RISC, so they're better, they have fewer instructions, so it's easier to work with. That's all crap, right? Reality is all of these instructions in the modern CPU are interpreted into microcode that does whatever the microcode does, and all of this RISC, CISC, whatever argument you heard in computer organization or in computer architecture or whatever is all complete bogus bullcrap. But the upside is we have really cool instructions to work with, like inc and dec. These are cool instructions. All right. Anyways, that's just we'll leave this at minimally modified for now. But you know, if you're a true X head, you would do dec R10, but it's fine. We'll sub. Okay, so here we have this guy. Okay, perfect. So here, our big loop, right off the bat, and this isn't quite num args, this is num files remaining, is in R10. And so this loop will say while num files remaining R10. This is the condition, right? And let's call this the looping, well, let's stick with our big loop, it's fine. Okay, so while num files remaining R10. Awesome. We still don't know what the hell this is, but that's fine. We keep going. Here, we compare R10 against 0 and exit if they're equal. Awesome, and that's this while. And let's see where we jump right to the exit, where we exit with a 0. Awesome, okay. So that all makes sense. Now we get into here. Now, it might be tempting to just read the assembly linearly. What's actually better is to jump around as you notice semantic anchors that you can anchor yourself. For example, I remember writing this code, and it also has comments that I wrote, right? And this, I remember, is our while header. Our while header is this while loop that reads from a file, and if it read 0 bytes, if the file is exhausted, it jumps to done, which is right after the while header. Otherwise, it writes those bytes to standard out and jumps back to the head of the loop. So let's rename this loop. I wrote this loop. We can rename this loop. Adam Dupay, the coolest cybersecurity professor at ASU, asks on Twitch, why are comments and code the same color? I don't know. This is some default Ubuntu configuration. We can try to change the, well, we're not going to do that, but we could. Anyways. All right. So let's take our while header and change it to output file loop. Awesome. Here we go. We got to change both. Output file loop. Okay. So now we've refamiliarized ourselves with the output file loop. All right. That all seems to be in order. Now what's left that we didn't read is what the hell this whole situation is, right? Of course, this whole situation is probably opening this file descriptor, right? So I'm going to make a comment, preliminary comment, probably opens a file descriptor, right? So how does it do it? Well, here, and by now, several sessions into Computing 101, I've memorized that syscall2 is open on x86-64 Linux. So that's cool. This is the open. RSI is the second argument to open. That is the mode or the flags with which to open. And 0 is open file and read only. We've done this before as well. RDI is the a pointer or the memory address of a string in memory that is the file name. So here it is being dereferenced out of RDI. So RDI should be an address that points to a memory location where an address is stored, and that address that is stored, it points to the string. And here we go. Here's how we compute RDI. So we move the stack pointer into RDI, and then we add R11 to RDI. And R11 here was 16. And that is where this node comes from. RSP at the beginning of the program has the address of the first argument. Boom. Awesome. Okay, now we know. All right, so we have the address of the first argument. We have the offset from the stack pointer, RSP, to the address of the first argument in R11. This is great. And then we move RSP into RDI. So RDI points at the beginning of the stack. We add R11 to it, so now it points to the first argument. And then we open. And if the open succeeded, so if the file descriptor returned was not less than 0, if it's less than 0, we jump to error. Otherwise, we put it into RBX. So here's what this is. It is FD, that's an RBX, equals open argv, basically more or less R11-ish, right? Or let's say R11 divided by 8. We haven't talked about point arithmetic, and we're not going to right now. So whatever, R11-ish. Somehow, sought into by R11. O read only. And there. And this is, let's separate this out. If FDRBX less than 0, exit, or whatever, error. We don't know what error is yet, but we can, of course, jump down and read this, and this exits 1. Cool. So let's just add that here. Exit 1. All right, awesome. So, and then otherwise, this ends up in RBX. Let's do that up here, just to keep things together here. RBX, and we're not clobbering RBX over here. That's fine. All right. So now the file descriptor is open. And so this our big loop is loop over arguments. Let's rename it now that we understand it better. Loop over arguments. Okay. Now we go through this output file loop. We just talked about it. So that's how RBX gets the file descriptor, and then it gets put into our RDI, which is the first argument of the syscall. Okay. Awesome. This is all very good. Now, when we're done reading, as we discussed, we jump to done. Done here. We subtract R10. I'd subtract 1 from R10. So what was this? This is after we're done reading a file. We subtract 1 from num files remaining, which was what is stored in R10. So let's say this does num files remaining R10 minus minus. And then we add R11. And this is basically our R11-ish guy that is the pointer. Sorry, this is obsolete now. Okay. Where was it? Right here. This is where the open happens. That R11 is the offset from RSP that's going to be used to open the next file. So R11-ish guy incremented somehow by 8. Okay. Whoops. And we jump back up to loop over arguments, at which point we check if we still have any num file remaining, and then open the next file. This all looks quite good to me. And we keep doing that until the loop guy exits, jumps to exit over here. And this exit will exit 0. Okay, this all looks great. So let's just assemble it. We run it. It outputs one thing and if you do 2 files, it doesn't work. So now we have to figure out why doesn't it work. First thing that I do personally is try to say, okay, is there anything obvious I'm missing? So let's strace this guy. Should read open flag twice. Instead, it open flags once. It reads, and then it tries to open some weird crap. And that's not good. So what happened here? Our next open failed. And when it failed, our error checking caught that and exited. So this syscall returned a -1 bad address because we passed some weird address instead of the address of a string. And our address here is hex 20,000. I have no idea why that's happening. And now the key thing is to understand what is going on. So one of 2 things could be happening, 3 things. So let's create 3 hypotheses. Okay. We're going to make a notes doc. Hypotheses. 1, the stack pointer is getting messed up. Why could this happen? I don't know, but it could be causing this because what we pass into open, what we know is by the end of this whole thing, RDI is hex 20,000, and it shouldn't be. RDI depends on a couple of things. It depends on what was stored at this load, and this load depends on this address, depends on the value of RSP and the value of R11. So RSP could have been getting messed up. R11 could be getting messed up. And what else? The value. So the pointer to the string, the address of the file name could be getting messed up. The actual memory contents that it reads from RDI. All of this could be happening. So now we're going to disprove it one by one. When we eliminate the impossible, whatever remains, no matter how improbable, will be our issue. So we're going to start I. I don't know why this doesn't say, but we're going to just IRIP. And we're going to basically actually disassemble the whole thing. Fine. We're going to look at 10 instructions. I want to understand right here, right when we compute this address. Yes, this is the, this is our open syscall. I want to break right here. And here, I want to figure out what RIP, sorry, I know what RIP is, what RSP, RDI, R11, and that value is. Just going to print out everything. Now, I could do this manually. Did you do breakpoints last time? Okay, so let's first do it manually. So I'm going to say break at this address, hex 401.015. Okay, that tries to look for a symbol name, something like loop over arguments. I could do break loop over arguments. That's awesome. And then I can hit continue here, and it'll run until it breaks here. And so this will be fine for now. And then I can step, and I can step, and it jumped to exit. Oops. So why did it jump to exit? Now I'm somehow in this exit 0 call. Well, it's because when I ran it, when I ran it, I didn't give it any arguments. Oops. Well, that's silly. So of course, our R10 starts out at 0. This is the num arguments left, and it exits right away. Okay, cool. Inferior process exited. Let's try this again. We're going to run. Now that we have a breakpoint already set, I'm not going to start I and break on the first instruction. It doesn't matter. We're going to just run straight up with the argument /flag. Let's do /flag and etc pass WD. Okay, here we go. Now, what is R10? It's hex 2. Let's step, boom. Okay, all is good. So now, what do I want to do? I want to display RSP, R11, and the result of RSP plus R11. So RSP, R11, and RSP plus R11. Let's see. Will this work? Well, this will work, sure. Yeah, that makes sense. RSP plus R11. So R11 is hex 10. That's our 16. That's great. 2 keywords. And then RSP is the base of the stack, and that works. And now I want to, and this unfortunately is a little bit of an awkward syntax. It's C syntax. So we want to display something that we're going to dereference RSP plus R11. I want to know what's stored there. The problem is when I do this, it doesn't know how many bytes to get out of what's stored there. So I need to give it a C type, which I will do unsigned long. This is an 8-byte, like this guy, integer. Boom. Okay. And this is what's stored there. That's a very weird address. Y is, we can also just xgx RSP plus R11. That's correct. Why doesn't it like this? This should have worked. Oh, yes. Unsigned long pointer. So I treat these as a memory address to an 8-byte thing. Boom. There we go. So this is what's stored there. And then this, whoops, it should be the address of our next string. And it seems like it might be. Awesome. That's the address of our first string. Okay, so far so good. All right, first loop, no problems. Then we're going to continue. Here are all my displays. I can undisp 6. This was a typo. I don't want to see it anymore. Okay. So here, something really weird. Is this really weird? This address looks strange because R11 is really fucked up. Why is R11 fucked up? So R11 started out as hex 10. And if you recall, if we get another SSH guy and we cat vi puppy.s, to R11 we added 8. That's all we ever do to R11, right? We move 16 into it. We use it as an offset, and we add 8 to it. And yet, when we go here, R11 got really messed up. It went from hex 10 to hex 20E. That's really not great. That's not good at all. Okay, So something is messing up R11. How do we figure out what? Well, we can run the whole thing from the beginning, or start it from the beginning. Actually, let's run it to the first breakpoint. So here we're about to open /flag. And now we're going to step instruction. We're going to keep an eye on R11. We'll figure out what the hell happened that it got messed up. So we step. So here's our, we're going to do our open. We do our open, and oh God, the open syscall destroyed the value in R11. Why would that happen? Well, there is an agreement that you have with the operating system, you as a process has with the operating system, called the Application Binary Interface, the ABI. Our part of this is the calling convention. So if you do x86-64 calling convention, okay, we can go on Wikipedia. Let's say there's one specifically for syscalls. We can go on Wikipedia. Or we can, MIT people probably know what they're doing, except for they're using fucking AT&T syntax, but that's fine. All right, the calling convention is defined in this crazy document. The caller uses registered specifies the first 6 arguments. Here are the registered. We know all of this stuff. Okay. The callee is responsible for preserving the values of registers RBP, RBX, and R11 to R15, as these registers are owned by the callers, by the caller. So that means that if we had stored a value in R12, it's up to us to save it. No, the other way around. The callee is whom we're calling. We are the caller. So the callee, the syscall, the kernel in this case, the Linux operating system, to whom we're begging, please open this file, will guarantee to us by contract, by this calling convention, that it will not fuck up RBP, RBX, or R12 through R15. But it gives no guarantees about R11. So R11 is up to us to save, right? We can do this. The typical way to do this is by pushing R11 to the stack and popping it off. We're not going to do that right now because I don't know what else we use the stack for in this super crazy thing. For example, we probably read onto the stack here, and yeah, for sure, we read onto the stack. So that's a bad idea anyways. Oh, well, we read 100 bytes behind us on the stack. But if we start messing with the stack and we're storing, we're reading data from the file onto the stack, and at the same time, we are pushing R11 that we want to save off onto the stack as well, because the kernel is going to clobber it. And then we read some data over R11, this is going to cause problems anyways. We'll end up with parts of the file in R11, and you'll see these sorts of bugs 2 modules from now in memory errors. But for now, we're just going to switch to R12, because R12 is one of these awesome registers that the kernel guarantees, or that the callees, well-behaved functions, also guarantee that they will not wreck. So instead of R11, we'll do R12. And actually, R10 is also susceptible to this. This makes no guarantees about R10. So we're also gonna change R10 to R12. I'm gonna use a regular expression here in Vim. I'm gonna change R10 to R12 and R11 to R13. Yes. Okay. And R11 to R13. Yes. Okay. Awesome. And now we're going to recompile it. Awesome. And let's see. Woo! Awesome. It works. You read multiple files. We've just recreated cat in 71 lines of assembly, including comments and everything. How cool is that? All right, so
You have one bonus detail. If you import the Felix cloud to your syscall instruction.
Oh, yeah, okay.
Totally the ABI's fault.
Oh, yeah?
Yeah. This is your x86, your favorite architecture.
So Connor claims, I have to remember. So Felix Clotaire has these awesome, basically parsed Intel instruction manual that explains what each instruction does down to like pseudocode. And if we search here for R10, R11, R11 gets your register flags, your conditional flags saved to it. Aha.
And RCX is also weird. RCX
and RCX
are just dangerous to use.
RCX also gets clobbered. Yeah, so, but it chooses these registers to clobber because it is not responsible for saving them, right? You will not see this syscall instruction clobbering R12, for example.
It's the little hardware that's doing it, not a convention that's doing it.
It is the
coupled together. Yeah.
Oh, it is the hardware doing it. Yeah, that's right. It is the hardware doing it. But also, this calling convention is defined by
understanding that
by a hardware by HTTP error 404. But yeah, that's a good point. So it's not Linux's fault necessarily. It's that Intel's x86 syscall instruction that's clobbering our registers. Okay, so now we have Puppy. Now we talked about obj dump. So we can disassemble Puppy. And sure, let's do in Intel syntax. These should be familiar. Loop over argument. Here's our loop over. This is our start. Here's our output file loop. Done, exit, error. All right, awesome. And we pass it into it. So, oh, great. So excluding comments, but including some of this new line crap. Puppy's 53 lines of assembly. So probably it's at 40 lines of assembly or so. Let's see what cat is. 4,280 lines of assembly. A lot of waste, right? So if it takes some amount of time for your CPU to execute every line of assembly, of course, not every assembly instruction in the file cat is going to be executed because like this probably eats up a lot of lines of assembly, the help output, et cetera, et cetera. But, you know, you can just see the difference in efficiency. Now, of course, anytime you add abstraction, cat isn't written in x86 assembly, it's written in C. And there are efforts to replace that even with a version of cat written in Rust, right? Because Rust, as we'll learn in a few weeks, is resistant to the type of errors where you accidentally clobber stuff on your in your memory space. Anytime you add these abstractions, you write something in C, you write something in Python, you write something in Java, you add more and more and more inefficiency, and in most cases, that's fine. In some cases, if you're a video game developer in the early 90s and you want to create something revolutionary and eke out every potential bit of performance out of the hardware, that's not fine. You need to do get pretty raw down into the actual. Or if you're, you know, building some embedded thing with a Raspberry Pi Pico or whatever, right? But most of the time nowadays, when you interact with assembly, you're going to be interacting with assembly either to operate in extremely constrained environments, like you have managed to fool a program into executing some tiny injected bit of assembly. You manage to inject it somewhere into its memory space. In those cases, you need to craft things very finely. Or when you're trying to understand what a compiled program does. For example, if we actually disassembled cat and tried to understand it on a low level, as we talked about maybe 3 sessions before. Okay, Yeah, and so as Honto says on Twitch, insert Roller Coaster Tycoon was coded in assembly. So was Transport Tycoon, awesome games. But what's interesting now, so Transport Tycoon originally was written in assembly. You can verify this. This game was amazing. I used to go back and like spend a week in inside this game every year. Transport Tycoon. You search for assembly here. It's part of an assembly language software. x86 doesn't. Oh yeah. So, anyways, it is written in assembly, but the Wikipedia page doesn't really talk about this much anymore. Came out in '94. Then it was gradually reverse engineered and re-implemented function by function into a game called OpenTTD, which exists today and is still very active and is awesome. But if you go and you look at TTD code, where's TTD code? We don't want to download it. TTD, OpenTTD, GitHub. If you look at OpenTTD's code, what's it's written in now? They implemented it function by function now into C++. Boom. It's not x86 assembly anymore. It's relatively modern C++ that allows them to move fast. They added abstraction as they no longer needed the insane performance improvements. I worked on games in high school in the late 90s, in the early 2000s, where most of the game was written in C, but like just the video code was written in assembly, right? So you reach for the tool that you need. An interesting thing here is if everyone properly supports the calling conventions, which instructions or which registers are used for arguments, and et cetera, et cetera, et cetera, then you can mix these languages quite well. Right? And this is how things like the function foreign interfaces between Rust and C, Python and C, and this sort of stuff works. Because a function implemented in a language shouldn't necessarily care what language its caller was written in, as long as they speak a common calling convention. Cool. Adam is trolling me on Twitch.
Is he saying you were writing assembly before most of the people in the class were born?
That's actually possible, but no, he's saying if I program on punch cards or stone tablets. All right, so that is a deep dive into a successful implementation of cat, first as kitten.c and then as puppy.s. Now we're golden. Okay. Now, this gives you a lot of what you need for building a web server. There's one concept that is missing, and this concept is forking, right? So you might have wondered, where do processes come from, right? In the Linux Luminarium, you have a shell, and you type puppy/flag, and puppy starts up as a process. And we can strace here. Puppy gets exec, and exec VE, I don't remember. Did I put an exec VE level into the Linux Luminarium? No, probably not. Exec VE is a system call that executes the program referenced to by path name. That was our puppy. It causes the program that is currently being run by the calling process to be replaced with a new program, right? So who's the calling process? It's our shell. And when we execute puppy, it exec VEs here. And in theory, according to the man page, our entire shell should go away and puppy should live in its place. But somehow that's not what's happening here. We still have a shell after puppy exits. So in Linux, every process begins life by exec. But and the exec morphs a process that already exists into a different process, wipes the board clean on it, except for its permissions, its capabilities, et cetera, its owner, groups, and so on, and its file descriptors, and just swaps in another process. But then why is there more than one process running on this Linux box? How does that happen, right? Well, it happens. Let's look at how it happens, actually. Let's strace, not puppy, but a shell. I'm going to do something crazy. I'll do that. I have a follow child. Here is the strace of this shell. And actually, let me exit the shell. I'm going to do something else. I forgot the syntax dash O. No, not capital O. Is it lowercase? Oh, yeah, dash O. Okay, we're going to strace. We're going to save our syscalls into this file. Okay, so here's my shell. Let's see if this works. How do I make it part of the screen on the right? I drag? I just drag.
Well, drag from the right to the left.
What?
There's no magic. Just do it manually. That's what I'm saying.
I'm dragging.
Pull from the right and make it smaller.
Oh, there's no magic?
Not on this.
I see. That's what you mean.
Get your own laptop.
I don't want my own laptop. I have a laptop. It just sec faults when streaming. Okay. So here we go. Okay, here's our shell. And we're gonna shrink this. Man, come on. How do you live in like the
my accounting 90s stuff?
Yeah, it's believe it when I see it. All right. And here we're going to cat our syscalls output. All right, so here's the syscall so far. And actually, already this is pretty funny. You can see we're getting a bunch of signals, these sig winch. This is winch stands for window change. A process gets a signal every time the dimensions of the terminal is running in change so that it can like adapt its interface and stuff. But that's fine. So we're going to tail syscalls here. All right, so now this guy's reading files, so we can hit enter here. So awesome. It read. Let's retail this. It read a new line and it wrote the prompt. You can hit enter again. It did that again and again. Awesome. Okay. What happens when I launch a program? So now I'm going to launch poppy /flag. Poppy ran. Okay. What happened here? It read in poppy /flag. It did something weird. It did a V fork. That's something weird. It did something weird again. Did something weird again. And then it ran this wait. And then it received a sig child. A sig child is sent to a parent when a parent process, when a child process does something. In this case, the child process exited. Okay. What the hell is a child process? Poppy was launched somewhere here, but we didn't see it. Why not? And what the hell is vfork? So these two things are related. So if we man vfork, vfork creates a child process and blocks the parent process. And you will be using an older, simpler syscall called fork. Fork creates a new process by duplicating the calling process. And the new process is referred to as a child process. So processes are like bacteria. When you call fork, they multiply by mitosis. Now you have two. After the shell forked, there were two shells, two bin-sh processes. And one of these processes said, all right, now I am going to become puppy. And if you look here, fork returned this guy, this value, and this value is the process ID of the new child process. And here's what it did. It did some cleanup, blah, 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 did some work, and then it executed puppy. And it became puppy for all intents and purposes. It ceased to be bin sh. Its memory space got wiped. It kept the file descriptors. That is, there's ways to make file descriptors go away, but it kept the file descriptors that were, let's say, just standard in, standard out, et cetera, et cetera. And now puppy is running after this. And puppy opens the flag, reads pwn.college, writes pwn.college, reads some more. That returns 0 bytes read, and so it exits. So processes start up when a parent process forks, and most common so far for you, that parent process has been the shell. It forks, and one of the copies that are otherwise identical, one of the copies decides, well, goodbye, I'm going to become puppy. How does that decision get made, right? How do you know which process is going to be which? Well, you know based on the return value of fork. The only difference between the two processes, other than the only two differences. One is that the child process, so, whoops, the thing stopped following me, but that's fine. I feel like you have the one process splits into two. Well, the process ID of the parent process sticks around with one of them. That's the parent process. The child process gets a new process ID, and that's the biggest difference from an operating system's perspective. From within the process's perspective, the fork system call returns into RAX. For the parent, the RAX becomes the process ID of the child. For the child, RAX becomes 0. So the child, after forking, can look at the process ID can look at the return value of the syscall, look at RAX, and if it's 0, it's the child. If it's non-zero, then it's the parent process looking. But otherwise, the process can't tell. As if you were suddenly cloned into the seat next to you in a split second, you would have to figure out who is the original and who is the clone. Or maybe you wouldn't. There's a very cool sci-fi by Alastair Reynolds called House of Suns, where the protagonist clones themselves like a ton of time, but does it in a way where it is impossible to determine who was the original. They wanted all of the clones to feel agency over their lives. Just pretty cool concept. Because typically in a sci-fi, like if you read like the Bobbiverse series, it's also about a bunch of cloning of intelligences, and there they explicitly know who the parent and who the child is, and so on. Highly recommend both books/series, by the way.
I think just to reinforce that, so all that changes is RAX.
Yes.
RAX register is the only different from all the other registers are the same. All of memory is the same. The file descriptors are the same. Everything's the same.
Cool.
Just RAX is different.
All right. So now we're going to write this in assembly and see. We're going to write a shell in 15 minutes in assembly, and it's going to be awesome. Okay, let's see if we can do it. All right. So shell.f. What are we going to do? We're going to read fork exec. Okay. So let's read. To be fast, move RDI. We'll read from standard input onto the stack directly. Gonna only support 100 bytes of things, and we'll only support like just argv0. All right. So move our spy, move our the x100, move RAX0, syscall, that reads onto the stack. Now fork, let's see what fork is from a syscall's perspective. Fork 57. Okay, and now after forking, one of us is the parent, one of us is the child. Okay, so the parent, so we're going to compare RAX to 0, and if it is 0, we are going to say child, otherwise we're the parent. And this is just for ease. Okay, and the child will exec. So the child will, let's look at exec, 59. So we need the file name, and then we need argv and then p. These can be null. These are the arguments. This is the environment variable. We're not going to support any of that shit. We're going to move RSP to the file name. RSI is going to be 0, and RDX is going to be 0, and we syscall here. And then the parent, so this execs out, and the parent is going to move, is just going to jump back to the start. Okay, looks good. This is our shell. We just wrote a shell and fucked in 2 minutes flat. All right. Okay, nothing works because we were using the evil AT&T syntax. Okay, so here's our shell. Okay, we didn't write out a shell, but let's run ID, and it didn't work. Okay. All right, no problem. Let's strace this to see what's going on. All right, so we read, we fork, and something went wrong. Let's strace -f, so we follow the children. So we read, we run a ID. For the record, ID, we lost connectivity here. ID returns your user ID and groups and stuff. So what's going on here? So we forked, okay. And our child started reading stuff. Okay, except the ID new line, no such file or directory. Aha! Okay, so we need to trim off the new line. That's okay. So here, when we did the read, we can just assume the last character is a new line. We'll just move. So we're gonna move into RBX, whatever, RDI. Okay, RAX is number of bytes. RSP is where we started reading to. We'll add RAX. This is now pointing beyond the new line, and we're gonna move into the byte pointer of RAX, RDI. Oh, we have to decrement RDI here. So now it's pointing at the new line, and we'll null it out. Okay, let's see. AS, NLD. And now, did it work? No. Okay. Let's strace it. Now we had ID. Okay, now we're ID, and now there's no such file or directory. Well, because if you remember from the linear there's this path variable, and the shell goes and look. None of that happens with execve. With execve, we actually have to pass the file, and it works. If you have a shell, we just wrote a shell in 4 minutes, and there's cool things that don't need arguments, like who am I? Awesome. We can launch bincat, and now bincat is going to just echo stuff out at us. Why is it echoing every other thing? Oh yeah, here we go. That's weird. There's probably a reason why it's out of order. But that's pretty cool. Yeah, the parent's also reading. So, the parent and the child have the same standard input and so forth. So there's a lot of wackiness. If you really want to be a good shell, the parent needs to wait on the child to complete, right? Because if I do like sleep 2 in a normal shell, it actually sleeps. But if I do in my shell here, sleep 10, and I look, it launched both sleeps. Where did they go? Oh, well, of course it doesn't support sleep 10 because it doesn't support arguments and it doesn't support a path. But we aren't waiting for the child to exit in a good shell. We should be. And this is actually very easy to see because if we do, like right before we read, we write a prompt. Let's do this. So let's move RSP byte pointer RSP. And RSP plus 1. We're going to build a little prompt here. And then RSP plus 2 will be 0. Okay, here's our little prompt. We're going to write move RDI 1, standard out, move RSI RSP, move RDX 3 bytes of 2 bytes of a prompt. Syscall move RAX 1 is right. We're going to build it. We're going to launch our shell. Boom, we have a prompt. But our prompt printed out before our program ran because the parent forks, and now there's a race going on between the parent and the child, and that's no good. So if we are a well-behaved process, if we're a well-behaved parent, we wait for our child. So here, instead of looping, we're going to call wait. And wait does a lot of scary things that we're almost certainly not going to be able to do in 4 minutes. Is there an easier wait? Is it wait ID?
Maybe it's that you pass null to everything.
All right, let's try that. We'll just pass null to everything. We'll pass the process ID, which was returned in RAX. That's how we know we're not the child. So the parent has the child's ID in RAX. So we're going to move that into RDI. We're going to move 0 out everything else. R8. R10. Okay. And what was the weight? 61. And we do a syscall. Okay. Boom. Boom. Whew! We waited for the parent. That's awesome. And of course, we can write a shell script that here is full bash. And it'll wait, and we can now see that we properly wait. So we just wrote a shell, a very, very simple shell that doesn't support program arguments and so on, in 49 lines of assembly, including some light comments and spaces and new lines, using fork and wait. And you'll need to do this. This fork is used by the shell, of course, but fork is often used by basically network servers like a web server to spin off a child process that handles an actual connection. A very common model is a forking network server, which sits listening on the network, and every connection that it comes in, it forks off a child to handle it. Conceptually similar to here, where every request that comes in, it forks off a child to become that request. Cool. You'll need to do that in building a web server. Now you know how. And that's all. Questions? No questions. All right. Let's wait a couple of seconds for questions on Twitch. Any final administrative things?
Assignment's due Sunday night.
Yeah. Assignment is due Sunday night. I guess, yeah. So for those like joining right at the end of today's lecture, what we did today, live debugging of a very interesting bug related to calling conventions, using some slightly advanced GDB stuff like this display thing, which, you know, lets us just rapidly step through things and notice when things change with our eyeballs. There are also ways to script that, which we'll probably deal more with in the next module. 2, we talked about fork and we wrote a shell. Anything else that we did? That's it.
Talked about video games.
And talked about video games a lot. Awesome. All right. Thank you all. Make sure to get those challenges in. If you haven't started on building web server, please start. As you can see, a lot of the concepts, a lot of the assembly wrangling can be done very rapidly once you get a hang for it. But you gotta first get the hang of it, and that can take days. So please, if you haven't gotten to building a web server, get to it as fast as possible and then get through it. All right. Good luck, and we'll see you on the other side. Goodbye, hackers.